Okay, good morning, everybody. So today we're going to try our best to finish up chapter 18, which we're dealing with enols and enolates. So how do we go about generating a kinetic enolate? What are the conditions we need to generate a kinetic enolate? Pardon? Okay, so we've got to be really cold. What else we got?
Polar aprotic solvent. A good non-nucleophilic base.
Okay, and what did you have to say, Sarah? We need a polar aprotic solvent, we need a strong non-nucleophilic base, and we need cold temperatures, right? All right, very good. Give me some examples of some strong non-nucleophilic bases. The LDA is the one that you need to go to, right? There are others. Now, one of your assignments was to tell me why the ketone that I drew on the board, if we used LDA, we got the kinetic enolate, but if we use sodium hydride, you got the thermodynamic enolate. What was the rationale for that? What did you discover? So the question is, why when we take this ketone and sodium hydride, THF, minus 78 degrees, why is it that we get the thermodynamic enolate and not the kinetic enolate? But if we used LDA, we got the kinetic enolate. Yeah.
Does it have to do with sodium hydride size in relation to LDA?
No.
Okay.
I thought that sodium hydride is not soluble in THF.
Exactly. And why is that the rationale? What does that explain?
It won't only react on the surface of the solid, and so the reaction is slower, and it gives it more time.
That's exactly right. So when Rose comes in and adds this ketone to this, the sodium hydride's not in solution. And so the ketone has to come into contact with the surface. So there's always the enolate present and the non-enolate form of the ketone. So you can think of that as the conjugate acid. And when we have the conjugate acid around with the base, they can equilibrate. LDA, however, is completely soluble in THF, and so as soon as the ketone hits the solution, it completely deprotonates, and there's never any appreciable concentration of the ketone present. So it can't equilibrate, okay? And so even though sodium hydride is a strong enough base, in theory, to generate a kinetic enolate, it almost always generates the thermodynamic enolate. Now, sometimes the thermodynamic enolate and the kinetic enolate can be one and the same, and in that case, sodium hydride will work just fine, okay? But it has to do with solubility. So a fourth rule would be then what? That strong non-nucleophilic base also needs to be soluble to generate the kinetic enolate, okay? Very good. All right, so we can generate enols and enolates, we know that now, and we can actually react those enols and enolates with a variety of electrophiles, and we're going to talk about reacting those enolates and enols with halogens so that we can replace the hydrogens on the alpha carbon with halogen atoms. And this works really well for chlorine, bromine, and iodine. Does not work for fluorine. As you can imagine, fluorine goes boom, right? So we're limited. And for all practical purposes, if you look in the literature, the vast majority of the time it's bromine. Not always. Sometimes you'll find iodine, sometimes you'll find chlorine. But bromine is typically the one that most people use in the literature. Can anybody tell me why? Bromine's physical state at room temperature is what? It's a liquid. It's easy to handle. Chlorine's a gas. Iodine's a solid. You might think, well, solids are easy to handle. And you're right. Not too bad. But it turns out that it's a lot easier to deliver the bromine than it is the iodine. And it's also, iodine is more expensive. So usually bromination is the way that we go. So if we take an aldehyde or a ketone that has at least one alpha hydrogen, we can react it with chlorine, bromine, or iodine in the presence of either acid or base, and we can get halogenation at the alpha carbon. We can replace carbon hydrogen bonds with carbon halogen bonds, and that has a lot of importance, okay? So we can make these halides very, very easily. So for example, Jamie could come in and take cyclohexanone, bubble through chlorine gas. For whatever reason, she decides that she likes to use gases. And she uses HCl and water to promote the reaction, and she can actually put a halogen on the alpha carbon. Okay? And then we can do all kinds of other things with that halogen, right? We could eliminate HCl to put in an alkene. We could react that with a different nucleophile that will react at the chlorine. We can do a variety of things. Could we take that halogen and convert it into a Grignard? We can, but what will happen? We've got a carbonyl, right? It's not that the carbonyl is going to get reduced, but once you generate the Grignard, that Grignard will react with another carbonyl. So it's not like you can have the ketone there and the Grignard at the same time. Okay? Chemistry will occur, but not the chemistry that you probably want. So how could we solve that problem? Let's say we wanted to generate a Grignard here and leave the carbonyl unaffected. How? You got the first part right. Now how are you going to protect it? How do we protect ketones? We could form an acetal. That's right. So we could convert the ketone into an acetal, do the Grignard chemistry we want, and then remove the protecting group later and get our ketone back. That's possible. Okay? So if you look at, we can take acetone, bromine in acetic acid. So we don't have to have a strong acid for this. You just need to have an acid conditions to generate a little bit of the enol. So we're under acidic conditions. Acetic acid is also a good organic solvent. And we can replace one of the hydrogens with a halogen. And the mechanism is exactly as you would think. We protonate the carbonyl. We tautomerize to the enol. The enol then reacts with bromine. So this carbon functions as the nucleophile, attacks one of the bromines. The other bromine leaves as a bromide. We end up here, the remaining bromide comes back, removes the proton, and we end up generating our alpha halogenated compound, or alpha bromoacetone, and HBr is the byproduct. Nothing new in mechanisms, right? We've talked about these types of mechanisms before. But notice it goes through an enol intermediate, not an enolate intermediate, and why must that be the case? Why don't we have an enolate here? Can we have an enolate under acidic conditions? No, because the enolate will get protonated, right? So all we can generate under acidic conditions is the enol, okay? So we can halogenate the alpha carbon, okay? So here's another example. We can take this dimethyl cyclohexanone. We can halogenate the alpha carbon. It doesn't matter which one because they're identical, right? And then we can actually treat this with a base, and we can eliminate a hydrogen from the beta carbon and the bromine from the alpha carbon, and we can put in a new functional group, a new alkene. This is probably one of the main reasons why people do the halogenation at the alpha carbon, is to introduce a alkene that is in conjugate resonance with the ketone or the aldehyde. Okay? It's a very, very easy reaction to do. You just need bromine, acetic acid, and then pyridine to do the elimination reaction. What kind of elimination would that be in that second step? Would that be E1 or E2? It's E1? So if it's E1, what's the mechanism? Okay, so the bromine would have to leave, right, and form a carbocation. So we would have a carbocation right here. Do you think that's likely? Okay, it's steric hindrance if, and you would be right, if the base had to attack this carbon. Which carbon does the base attack? The hydrogen's on the beta carbon, right, which isn't very hindered, really. Now, if we think about this being an E1 elimination, this halogen would have to leave and put a carbocation there right next to an electron withdrawing group. Would that be stabilizing or destabilizing? Destabilizing. So this is actually an E2 elimination. So the pyridine comes in, attacks one of these hydrogens. Those electrons go here to kick out the halogen in a concerted E2 type fashion. Okay? So it is an E2 elimination mechanism to get these alpha beta unsaturated ketones in this particular case. Okay? So I want you to take a couple of minutes, work with your partners, and work out these two problems. All right, let's walk through them together. Let's look at the first one. What steps do I need to take? I need to add a halogen to an alpha carbon followed by an elimination, right? But I have two alpha carbons. So what conditions do I need to put the halogen on? Kinetic or thermodynamic? Thermodynamic. So what might those conditions be? Room temperature, bromine, and acid, right? These are going to be thermodynamic conditions. We're going to generate the thermodynamic enol, which reacts with the halogen. And we're going to get this. Now, Gabby, what do I need to use to do the elimination? Pardon? Pyridine? That'll work. Do not use a Grignard. And you'll do the elimination. Okay? The second one looks a little stranger. What's strange about it? It looks like what we're doing is replacing the hydrogen on this alpha carbon with a halogen directly, right? What's the problem with that? We have not taught you how to do that, right? This is not an sp3 hybridized carbon. We cannot generate an enolate here. It wouldn't be in resonance with the carbonyl because that hydrogen is, if this is the plane, the carbonyl plane is like this, so they're orthogonal to one another. You can't draw resonance structures. Remember, we can pluck off those alpha hydrogens because we can draw resonance structures with the carbonyl. Can't do that here. But you have all the tools in your toolbox to do this exact reaction. So, what can we do to alkenes? Because we're starting off with an alkene, right? What can we do with this alkene? That's right, we can do addition. What can we add across that alkene? We could, but is that going to get us where we want to be? I can add bromine. That's right. So I can take this molecule, react it with bromine, and what does that give me? A dibromide, right? All right. Get bromine there. I get bromine there. So now I've got the bromine exactly where I want it, right? But I've got an extra bromine, and I lost my alkene, so now what do I do? How? What do I need to do? What's that? Okay, we can use a base, right? And do an E2 elimination. Having said that, tell me why this bromine remains, and I eliminate this hydrogen I eliminate this hydrogen and this bromine to give the product. Why couldn't I eliminate this hydrogen and this bromine to give the bromine down here? I can draw a mechanism, right? I don't have a carbocation in either case. Primary, well, it wouldn't be primary. It'd be an sp2. The answer's real simple. Huh? There are fewer hydrogens, and there's 2 hydrogens here. How does that matter? So why do I eliminate the single hydrogen and not the one of the 2 hydrogens? What's the difference in those hydrogens? Pardon? It's acidic. That's right. This hydrogen is on the alpha carbon. What is the rough pKa range for a hydrogen alpha to an ester? About 25. What do you think the pKa of these are going to be? Higher than 25 or lower than 25? Higher. What will a base react with first? The most acidic hydrogen, right? And so the base comes in, reacts with the acidic hydrogen, and that's the mechanism that occurs. But on paper, I could have just as easily drawn the mechanism where the pyridine comes in and gets one of these hydrogens, these electrons come here, and that leaves. But it's all about acid-base chemistry, okay? I wasn't joking all those times that I said, if you understand your acid-base chemistry, you'll understand most of this stuff, okay? It really comes down to what's most acidic, what's most basic, what's the better electrophile, what's the better nucleophile, okay? And so you can use these types of processes to answer these questions. All right. We can take propiophenone and we can react that with bromine under basic conditions, and we won't just replace one of the hydrogens, we will replace both of them. Whereas in all the acidic conditions that I was showing you earlier, we just replaced one hydrogen with a bromine, right? Why is it that under these conditions we replace both hydrogens with a halogen? They are both acidic, that's true. They're both alpha hydrogens. That was the same argument under the acidic conditions, though. Okay, that's not too far off. Let's work through it. So Sarah comes in, she takes her molecule, propiophenone, and she treats it with a little bit of base. What does she get? We're going to get an enol or an enolate. We're going to get a little bit of enolate, right? And we're going to replace one of the hydrogens with a bromine. Is that remaining hydrogen more acidic or less acidic than the hydrogens here in the starting material? What do you think, Nick?
More acidic,
And why?
because there's less hydrogens on the carbon.
Okay, but I can draw something on that carbon that would have less hydrogens that it would actually be less acidic. So what is it about the halogen that's making that hydrogen more acidic? See, we replaced one of the hydrogens, put a bromine there, and now this hydrogen is more acidic than in the starting material. Why is that? The bromine is electron withdrawing. That's right, it's electronegative. And so what's the effect of that on the acidity of that alpha hydrogen? It increases the acidity. That's right. So this is going to react now with additional base and generate the enolate again a lot faster than we did here. Okay? So once you generate the product is more reactive than the starting material, and it reacts, and it will get halogenated. Okay? And so under basic conditions, very important, you need to mentally write this down. Under basic conditions, you will exhaustively halogenate the alpha carbon. By that I mean you will replace all the hydrogens on the alpha carbon with halogen. Under acidic conditions, you can stop after monohalogenation. Now, if you're patient and you wait several days under acidic conditions, you can do the same thing. You can exhaustively halogenate. But it's slower under acidic conditions. So if you want to put a single halogen on the alpha carbon, you need to use acidic conditions. If you want to put all halogens on the alpha carbon, replace all the hydrogens with halogens, you need to use basic conditions. Okay? And that's always because the products are more reactive than the starting materials. Okay? Now, this has consequences in what's known as the iodoform reaction. Has anybody read that in the book? Anybody know what the iodoform reaction is? If we take something like, let's say, acetone, and we treat it with an excess of iodine under basic conditions, and I'm just going to write excess here, what we get is a molecule called iodoform, which is a solid, and it's yellow, and it precipitates out of solution. It is an excellent test for the presence of methyl ketones. Okay? The iodoform reaction. What else is interesting about this reaction? What did I just do? I converted a ketone into what? Pardon? Well, it's not an alkoxide. It's a carboxylate. It's almost a carboxylic acid, right? So if I protonate this by dumping in an acid, I can make carboxylic acid. So I can actually take ketones, if they're methyl ketones, and can convert them into carboxylic acids in iodoform. Okay? Now, this has practical consequences for you all in terms of your domestic drinking water. What do they treat domestic drinking water with? Chlorine. Okay? And so the same thing can happen with chlorine. Except you get chloroform, not iodoform, which this is a liquid. If you ever look at an EPA report on your domestic drinking water, they test for chloroform. And many people think, oh, that must be because of some industrial activity. No, it's because we typically get our drinking water from a domestic source that's contaminated with organic materials from biological organisms, okay? And there are methyl ketones that are contained in those materials. And then when your water treatment plant starts to treat it, try to kill all that stuff with chlorine, they do generate a little bit of chloroform in that process. okay? Chloroform is a carcinogen, and that's why the EPA tests for it. Not because there's somebody downstream dumping chloroform in your drinking water. It gets generated through this process, okay? That's why your Brita filter will tell you how efficiently it can remove halogenated compounds, and by that they mean chloroform, okay? Because we treat our domestic drinking water with chloroform, or with chlorine, excuse me, and it can generate trace amounts of chloroform. So why would we want to risk having a trace amount of a carcinogen in our drinking water? That's right. We don't want to get dysentery, right? So your risk of getting cancer from drinking that trace amount of chloroform is much, much less than your risk of dying from dysentery, okay? So it's a trade-off, okay? How does this reaction work? Let's take the iodoform reaction. How does it work? I'm under excess iodine and I've got basic conditions. So what am I going to do to one of these alpha carbons? I'm going to exhaustively iodinate, right? Okay. Now what happens? How do I take that molecule and get the iodoform and the carboxylate? What has to happen? Hydrogen? All this? Okay, so I've got sodium and I've got hydroxide, so tell me how that happens. You're right. Just do the math, as they say. How do we do it? Okay. Now what happens? What do you think, Jamie? What happens now? We're at the tetrahedral intermediate. What has to happen? Here? Okay. And what else has to happen? That's right. What's weird about that step? What are we breaking? We're breaking a carbon-carbon bond. That's not typical, right? Unless it's a pi bond. But we're breaking a carbon-carbon sigma bond. That's a little unusual. Which this now then comes in and reacts, and I get the iodoform and the carboxylate. Why is this a good leaving group? Most of the time I've taught you that carbanions are not good leaving groups because they are what? They're negative, that's true, but halogens are good leaving groups and they're negative. Typically, carbanions are poor leaving groups because they're strong bases. Is that a strong base? Ci3 minus. Why not? It is not a strong base. Why is it not a strong base? What are the iodines? Are they electron withdrawing or electron donating? Withdrawing. So I've got this negative charge with these 3 electron withdrawing groups on there. Does that stabilize the conjugate base or does it destabilize the conjugate base? It stabilizes the conjugate base, which makes it a weaker base, right? And so this is one of those situations where we're breaking a carbon-carbon sigma bond because this anion is so stabilized by those 3 halogens. And that's why it occurs, okay? That's known as the iodoform reaction.
When water is fluorinated, does it undergo the same process?
Water is fluorinated with fluoride, so F minus, not F2. So no, it will not undergo. But they do treat water with Cl2. So if you've ever been to a water treatment plant, I worked at an environmental lab when I was an undergraduate for 2 years. We had to go to these water treatment plants, and you walk in and there's literally a tank of chlorine gas with a hose, and it goes through all this stuff and it bubbles the chlorine through it. And so they treat it, filter it, put in, and what's coming out the end is chlorinated water, but there's a trace amount of chloroform in there, and we actually had to test the water for chloroform presence. And it was, I forget exactly, but it was in the part per billion range, something like that. Very low concentrations of chloroform. How would you take that small of an amount of material out of it? It's impractical to distill it out because you've got millions and millions of gallons of water, and it would cost lots and lots of money to distill that much water. So that's not very practical. So what you do is you put a filter on your house, a Brita filter or whatever, and that's how you get rid of the trace chloroform. Right? Most refrigerators these days have filters built into them that will remove the chlorinated products. But I would much rather drink chlorinated water than take my risk with fresh stream water and die of dysentery or whatever else the case may be. So. Now, we can use enols and enolates to make carbon-carbon bonds. So, for example, if we take a ketone, as we have here on the slide, we treat it with LDA, THF minus 78 degrees. We're going to generate what enolate? Kinetic or thermodynamic? Kinetic, right? And so we get the kinetic enolate here, okay? These things don't mean anything, okay, so on this particular example. So now we have the enolate, and we can react that with alkyl halides and make new carbon-carbon bonds. It's just a simple SN2 reaction, okay? So enolates can react with alkyl halides to put new carbon-carbon bonds. So for example, if we take acetone and treat it with LDA at minus 78 degrees, we generate the enolate. In this case, the kinetic and the thermodynamic enolate are one and the same because you can only do one type of deprotonation. And then we could bubble through methyl bromide gas, and we can make a new carbon-carbon bond through an SN2 reaction. Okay? Why is this important? Because we're forming carbon-carbon bonds. I told you there's only a handful of ways to do that, right? We learned how to make carbon-carbon bonds with Grignards. We've learned how to make carbon-carbon bonds with the Diels-Alder reaction. And now we're learning how to make carbon-carbon bonds with carbonyl-containing compounds through their enolates. Okay? Another example is to take cyclohexanone, treat it with LDA, THF minus 78 degrees, generate the enolate, react it with this, what's known as allyl chloride, because it's the allylic position, and we can form a new carbon-carbon bond here, and at the same time introduce a new functional group. Okay? So all the things that we've learned about SN2 chemistry starting to come back again, right? So enolates and alkyl halides make asking for an answer. An enolate and a alkyl halide makes a new what? Carbon-carbon bond. An enolate or an enol and a halogen makes a new carbon-halogen bond, right? You need to know these things at that level. If you don't remember the mechanisms, you need to at least remember what's the transformation is going to be, right? Then you can work through the mechanism if you need to. But it's just a simple SN2 mechanism, okay? Now, if Gabby came in and took cyclohexanone, treated it with LDA, THF, minus 78 degrees, and then dumped in, after the enolate was formed, iodoethane, she would make a new carbon-carbon bond and a new stereogenic center, because this carbon has 4 different things attached to it, right? It's got the ethyl group, it's got a methylene, it's got a hydrogen which isn't drawn in, and it's got a carbonyl. That is a chiral center, or a stereogenic center, right? And the 2 enantiomers actually turn out to be formed in equal amounts. Can anybody tell me why? Why will she get a 50-50 mixture of both enantiomers? Pardon? That's correct. And why is that the case? It's planar. That's exactly right. Once we generate the enolate, if we look at it and draw the resonance structure, we notice that that carbon is planar. It's sp2 hybridized, right? And it's planar. And so the probability of coming in from the top and the probability of the electrophile approaching from the bottom is 50-50. And so we end up with achiral starting materials will always give us racemic mixtures when they generate new stereocenters in the reaction. Okay. Now we can use conditions to determine where that new carbon-carbon bond is going to be formed. So if chance comes in and takes this methyl cyclohexanone, this 2-methyl cyclohexanone, we have two different alpha carbons. We have the alpha as shown here, and we have the alpha with the methyl group. And if he takes this molecule and generates the enolate under kinetic conditions, he will generate the enolate at what is labeled as the alpha carbon, the least substituted, right? That is the kinetic enolate. So he has this at low temperature, and then he adds iodomethane at really low temperature, and he will get this product exclusively, pretty much. There may be a trace of the other product, but 99.9% of it will be this. And so he's just put a methyl group on the carbon that didn't contain a methyl group before. However, I can take the same starting material, and I can ask Gabby to generate the thermodynamic enolate by changing the conditions, right? And how would she do that? She would use a polar protic solvent, she would use a weaker base, and she would use room temperature. And so she could generate the thermodynamic enolate, then dump in the iodomethane and make the carbon-carbon bond at a different location. Conditions matter because we can generate kinetic and thermodynamic enolates, okay? What would happen if Chance generated his kinetic enolate and let it warm up to room temperature and then dump in his iodomethane? We would get the thermodynamic product, right? To get the kinetic, you always have to be at low temperature. You have to keep it at low temperature because if we let it warm up, it will eventually equilibrate to the more thermodynamically stable enolate. Okay? This type of chemistry is used in the pharmaceutical industry. You all have enough knowledge right now that you can go in and make tamoxifen. Does anybody know what tamoxifen is useful for? For what cancer? Not leukemia. It's one of the go-to drugs for breast cancer. And it has a lot of success in treating breast cancer if it's caught early. Okay? I don't think it works as well in males because male breast cancer is extraordinarily aggressive. Okay? But in females, it works quite well. Okay? Has a very high success rate of working. It is a simple molecule. Look at tamoxifen. You can tell me all of the functional groups that are in there. Tell them to me. What kind of functional groups do we have? Pardon? Yeah, we got an alkene. What else do we have? We've got an ether. I heard that. What else do we have? We've got some aromatic rings. And we've got a tertiary amine. That's exactly right. You all have learned all of these reactions. You know how to make alkenes. You know how to work with aromatic rings. You learned just the other day in lab how to make a tertiary amine, right, using the Eschweiler-Clark procedure. You've learned how to make ethers. You've learned all these things. Tamoxifen is a billion-dollar drug, and it's made with nothing more than sophomore organic chemistry. They start from extraordinarily cheap starting materials. They start off with this ketone that already has 2 aromatic rings that we need in the product, right? They treat this with sodium hydride, which is a what? It's a base. Pretty strong, right? What kind of enolate will it generate? Thermodynamic, does it matter here? We've only got 1 alpha carbon. It can only generate 1 enolate, so it doesn't matter. They generate the enolate. They then put in the ethyl group by simple, what kind of chemistry is that? It is acid-base chemistry, but what would the name be? What kind of reaction is it? SN2. A simple SN2 reaction puts in this new carbon-carbon bond that they need. Notice where the ethyl group is, right? And so now they've got the ethyl group in, they've got the two aromatic rings, right? Now several steps they get to this. Now let's talk about those several steps, right? Tell me how you could give me those several steps. How do we get the other aromatic ring in? Matthew Hassler? Use a Grignard. That's exactly right. What Grignard did they use? Obviously they use, what is that? Yeah, the exact one that you all made, right? You all made the phenyl magnesium bromide in lab the other, or whenever it was, right? So, right, we take the Grignard, we do an attack on the carbon of the carbonyl, and what do we get as a product? A tertiary alcohol. So we have an alcohol here, the new aromatic ring. How do we get the alkene? We remove the alcohol and the hydrogen as water. How do they do that? They use dehydration. What do we use for dehydration? They use sulfuric acid. Voila, they put in the carbon-carbon double bond. Okay? Now what do they have to do? They have to remove this bromine, and they have to convert this ether into this ether. Okay? So how could we get rid of this bromine? Matthew Hassler? I'm serious. Not use a Grignard, make a Grignard. That's right. We could react that molecule with magnesium and ether, make the Grignard, right? And then they simply dump it into water, and that replaces the bromine with hydrogen. It's just that easy, right? So they remove the bromine. I've always wondered why in the world they had to have the bromine to start with. I've never figured that out, but they do. Then how do we convert this ether to this ether? We got to remove that methyl group, right? How do we remove a methyl group in a methyl ether? If I take that ether and I boil it up in HBr, I will remove that ether. And I will end up with the phenol. Then you simply take the phenol, you react it with a base to make the phenoxide, which is a nucleophile, and you react it with the alkyl halide of this molecule. And you've just made tamoxifen using nothing more than sophomore level organic chemistry. There are no real stereo centers in terms of chiral centers, but we do have to worry about the configuration of the alkene. These two aromatic rings have to be, how would these be related to one another? Trans, okay? And these two have to be cis. And that's where some of the trick comes in too. They have to play with some conditions and make sure it's that, okay? But on paper, at least, you all could sit down and draw out the entire set of reactions that you need to make tamoxifen, which is a multi-billion-dollar drug to treat breast cancer. If any of you have known somebody that's had to undergo chemotherapy for breast cancer, chances are they've had tamoxifen treatment. Not always, but chances are they've probably had tamoxifen treatment. And it does have a high level of success. Pardon?
So do you want to start a company?
There's already a company that does it.
Yeah, but we could do it and undercut the price.
They may still be on patent, I don't know. Which means you undercut the price and then you go to court, right?
Move it to China.
Move it to China.
Force it.
The malonic ester synthesis is, again, using enolates, but those enolates are derived from malonic esters. So this is malonic diethylmalonate, diethyl malonic acid ester, basically. These alpha hydrogens, are they real acidic or just kind of acidic or not acidic at all? Remember that table we had? They're going to be pretty acidic, right? Because they not only have one carbonyl, they got two, right? And so we can generate the enolate very easily. And I usually use sodium hydride when we do this in our laboratory. And we can alkylate these with just iodomethane or some other primary alkyl halide, works really well. And we can make new carbon-carbon bonds. And for what we do in my lab, that's good enough. That's what we need. We need these diesters, as we call them. But you can actually take these diesters and you can convert them into carboxylic acids. This is another way of making carboxylic acids. I want you to think about how we go from these types of structures to the carboxylic acids for Monday. I want you to write it down, okay? How do you go from this, basically, to the carboxylic acid that's drawn there? Okay? So look up the malonic ester synthesis in your book. You can use your online resources. It's going to show you that several things that we've talked about are coming together. Acid-base chemistry, decarboxylation, the whole 9 yards. Okay? So does everybody have their stuff that I told them to work on? All right. Make sure your name's on it.